Alright, so based on the autoencoder model we provided in the previous pages, actually we can have different variants of autoencoders as well, which can address some of the shortcomings with autoencoders we mentioned before. Before then, we have to introduce the regularization terms for model sparsity controlling first. So we have been using these regularization terms in model learning a lot in the previous lectures, right? If you still remember, when we talk about these regression models, we have been using these regularization terms in defining both the rich as well as regression models for you, right? So in controlling the sparsity of model variables, we have to add some regularization terms into the loss functions or into the objective function instead. So we can define the regression terms by using some norms on the vector. So before that, we still need to do a revisit of the vector norms or matrix norms. So we have also talked about this before, right? If you still remember, we have some coloring pages about the vector norms. So we can define an LP norm on vector x input as the summation of its contents raised to the p's power. We have the absolute value here, and then further calculate its p's root instead, right? So this p can be some integers. We have p equals to 1, equals 2, equals infinity, right? And we can define different kinds of norms instead. So here we show you the L1 norm, L2 norm, and the L infinity norm, and at the bottom. So the L1 norm, it will be equal to the summation of all the absolute value of all its elements, right? And the LP norm of the vector will be equal to the square root of all the element squares. And the L infinity norm on the vector will be equal to the maximum value of its internal element absolute values, right? And we'll provide you with some examples given the input like x equals 1 to -3. Then we can calculate its L1 norm, L2 norm, L3 norm, and L infinity norm as shown here. So if you still remember, when we talk about the regressions, we also provide you with two varieties of regression models, right? Compared with linear regression. So the main difference, compared with linear regression, lies in the objective function. Besides the loss term, we also added some regularization terms on the coefficient of the model into the objective function, like w as shown here, right? For the rate, we use L2 norm. For the loss, we use the L1 norm instead. And you may wonder why we have to add this. And why we have to add this? So actually the main reason or the main motivation to add this regularization term is to ensure the sparsity of these model parameters. And why we have to control this model variable sparsity, you may wonder, right? And in this page, we show you with some examples about overfitting to show you the motivation why we need to control or recognize these parameters inside the model. And let's assume we have some data sets, and we want to draw a curve to fit the data sets. And denote this data set by the dots in the feature space, right? So we have so many data points as shown here, and we want to draw a function to fit this data set, as better as possible. So there are different ways to define this function, right? And someone may say we can define one single linear function. We can just draw one line to fit the data set to ensure we have as more points lying in this line as possible. Right? This linear model will have very few parameters, right? In other words, for this linear model, we don't need to consider overfitting problems actually in most of cases. Someone said we can learn a function like this curve to fit the data set to ensure almost all the points will be incident to the line curve. So by learning function like this, we can ensure we can achieve very nice training loss, right, on the training set, because we can ensure all the points we see in the data set in the training set will be lying in this function curve and introduce very few loss terms, right? In other words, when we are fitting a function like this, we can achieve very good performance in the training set when we are training the model, because we ensure we achieve almost zero loss for all the training data points. Then you may wonder, if we have a function model like this and we try to use this function to further apply them to a test set, how will be the performance? Because we fit the data set or we fit the training set too well, right? We may name this one as overfitting. We overfit the training set. This overfitting may achieve very good performance on the training set. However, when we apply them to a testing set, then the testing performance will be very bad. Because we fit the training set too well, and we incorporate too many parameters in the model, right, to define this function curve. So this model will have very bad generability, right? In other words, it cannot handle many other unseen data points very well. If we have some data points here, then it will create a very large notch term, right? Similarly, if we have a data point here, then it will also create a very large notch term as well, right, for the testing set. We name this one as overfitting. So compared with overfitting, then for this simple case, if we draw a very simple function curve, then this one is called underfitting, right? Underfitting. Then you may wonder, how can we learn a very good model, which is a good fit or robust? So the way we learn a very good model for the regression task as shown here is to consider to utilize some regularization terms on the model parameters. So formally, when we consider some regularization terms, we can define the object function to be the notch term plus the regularization term on the parameters of the model, right? It will be similar to the range and the nutso as shown here. So by considering this regularization term on the parameters of the model, then we can balance between the notch term and the regularization term, right? We want to ensure the model can learn very sparse parameters to control the number of parameters which will take effect to define the model or to define the function curve, right? If we use very sparse parameters to define the model or to define the function curve, then we cannot draw some curve like this, right? Because this one may require some many parameters. Then we can learn a function which can generally fit the training set, right? To ensure we can generally fit the training set and introduce as no notch function as possible with a balance between notch and the parameter regularization, right? So it can help us to learn a very good fit, for the training set, and also can achieve very robust performance for the testing set. This is the general idea to consider to add these regularization terms on the model parameters. And for the autoencoder model we started in this section, we may also consider to add some of these regularization terms on the model architecture as well, on either the non-representation or on some other parts. We'll show you later.